we're going to talk about exponential population growth. So last class we learned about linear growth models where you add the same amount at each transition. So that's the definition of a linear growth model. You're always adding the same amount. And linear growth always results in something called an arithmetic sequence. And we also learned a little shortcut for how to add up the numbers in an arithmetic sequence. Okay, remember, add the first and the last term, multiply by the number of terms, and divide by 2. All right, so today we're going to move on to a different kind of model, an exponential growth model. And in an exponential growth model, you multiply by the same amount at each transition. So it's different from linear in that in a linear model, you always add the same thing. In an exponential model, you always multiply by the same thing. Exponential growth results in something called a geometric sequence. So here's an example. We have a rabbit population that starts with 1,000 rabbits and increases by 20% per year. Let's see how many rabbits there are after 1 year, 2 years, 3 years, and years. So we will have n, and we'll call this P sub n for population in year n. In year 0, how many rabbits are there? 1,000. That's how many we start with. Okay, 1 year later, we have to increase this by 20%. How do you increase a number by 20%? Multiply by what? 0.2. Okay, so if I do 1,000 times 0.2, what do I get? 200. That's good, 200. So do I only have 200 rabbits next year? How many rabbits do I have? 1,200. You have to add that 20% of 1,000 to your 1,000. So I have 1,000 plus 200 more, which is 1,200 rabbits. And just as a quick side note, how can you come up with 20% of 1,000 really fast without using a calculator? Yeah, like 10% is 100 and double it. Yeah. So 10% is easy because it just moves the decimal one to the left. And then but we don't want 10%, we want 20%, and 20 is twice 10, so you double it. That's also a quick way of calculating tip in a restaurant. Take 10% and double it if you want to leave 20%. All right, year 2. So I have 1,200 rabbits now. I have to increase that by 20%. So 10% of 1,200 is 120, and then double it is 240. So I have to add to my 1,200 that I already have, I have to add 240 rabbits. So that's 1,440. Year 3. I have to increase 1,440 by 20%. So I take 10%, which is 144, double it, I get 288, and I have to add that to 1,440, and now I'm getting where I have to carry, right? So I'm just going to use my calculator. 1,440 plus 288, 1,728. Okay, so I can do this year after year, and this is resulting in something called a geometric sequence, because to get from 1,000 to 1,200, what do you multiply by? Well, 1,000 times 0.2 is only 200. 1.2, 1.2, because I want to keep 100% of it, so that's the 1, and add another 20%, so that's plus the 0.2. So if you multiply by 1.2, 1,000 times 1.2 gives you 1,200. And then same thing here, 1,200 times 1.2 is 1,440. Keep 100% of what you have plus another 20%. So the 1 represents the 100%, 0.2 represents the additional 20%. Right? And then 1,440 times 1.2 is 1728. So for step n, okay, in year n, how do I get the population in year n? We can write a recursive formula. Yep, just take whatever you had the year before and multiply by 1.2. Okay. Or, right, if I want to write an explicit formula instead of a recursive, so I'll put recursive here. What makes this formula recursive before we go to the explicit? The p sub n minus 1. I had to know the previous term to get the next term. When I write an explicit formula, I don't need to know the previous term. So if I want an explicit formula, I'm going to use the fact that I'm starting at 1,000 and repeatedly multiplying by 1.2. So I'm going to say, well, I'm going to start at 1,000 and I'm going to multiply by 1.2 repeatedly. And how do we indicate, like, what mathematical operation do you use to indicate repeated multiplication? Exponents. So how many times do I multiply by 1.2? However many years it is. So this is going to be 1.2 to the n. And this is my explicit formula. Okay, so recursive, just take the previous year, multiply by 1.2. If you wanted to write an explicit formula, you can say, well, start at 1,000 and multiply by 1.2 n times. So the number 1.2 in this problem is called a common ratio because it's the value of the ratio of the current population to the previous population. So if you do 1,200 divided by 1,000, you get 1.2. 1,440 divided by 1,200, 1.2. 1,728 divided by 1,440, you get 1.2. Take any two consecutive years, if you divide their populations, you get the 1.2. So if I wanted to confirm this, I would write, okay, 1,200 over 1,000, that's 1.2. 1,440 over 1,200, let's just double check in the calculator. 1,440 divided by 1,200, yeah, we get the 1.2. All right, so these are the general formulas for exponential growth models. Again, just like with the linear, we just did a problem where I wrote the explicit and the recursive formula without knowing the general formulas. So you don't have to memorize these, but it could come in handy, right? Maybe you just like to have the security, having them on your cheat sheet for the test. So for recursive formula, you have to give the starting amount, right? Otherwise, it's impossible to get to the next value. You have to have some place where you start. And then p sub n is equal to p sub n minus 1 times the common ratio. So in our case, that was 1.2. And then for explicit, p sub n is equal to the starting amount. In our case, that was 1,000 times the common ratio, which was 1.2 to the n. All right, so here's a little bit of a different kind of setup that's also exponential growth. The Earth's population was about 6 billion in the year 2000. And assuming the population doubles every 45 years, project the population in the years 2045, 2090, 2450, and 2900. Take a few minutes and think about this one in your groups. All right, so let's go through it together. So Earth's population, 6 billion in 2000. So we're going to have n and p sub n, okay? And I'm going to use year 0 to represent the year 2000. It's just a way to make the numbers smaller so our calculator can deal with it. So we're just going to start counting at the year 2000. So this is the year 2000. Population is 6 billion. Okay. So in the year 2045, that's 45 years later, right? What's the population going to be? 12 billion, because every 45 years, the population doubles. Okay. So, and then in the 2090, what's my population? 24, because the population will double again. Another 45 years has gone by, population doubles again, and I get 24 billion. But then there's a bunch of blanks here, right? And I go to 2000, the year 2450, 450 years after the year 2000. How do I figure that one out? Okay, so from just a couple of different approaches that I saw, one common one was to say, okay, from here to here, how many years have gone by? 360. So from 2090 to 2450, 360 years have passed. How many sets of 45 years are there in 360? 8. Okay, so that means that my population should double 8 times between 2090 and 2450. 360 years, that's 8 sets of 45, so the population doubles 8 times. So to get from here to here, I should multiply by 2 8 times, which is the same thing as multiplying by 2 to the 8th. Right? Because multiplying a number by itself 8 times would be an exponent of 2 to the 8th. Okay, so another popular approach was to start in year 0 and say from year 0, or the year 2000 to the year 2450, how many years have passed? 0 to 2450, how many years? 450. How many sets of 45 are there in 450? 10. So from here to here, there's 10 sets of 45. Okay, so if I start with my 6 billion, then I would double 10 times to get to 2450. So either approach is going to give you the same answer. Let's just type it in here. All right, so I want 6 times 2 to the 10th, and I get 6,144 billion. That's 6,144 billion. Okay, or I could start with 24, and I would double only 8 times. So I multiply times 2 to the 8th, and you get the same answer. So 6,144 billion. We'll just leave it in billions. Or you could write 6.144 trillion. Some people were writing out zeros or using scientific notation. All fine also. All right, so then the next thing they want me to find is what is the population in the year 2900? 900 years after the year 2000. How could I figure it out? I'm going to give you a couple minutes to think about it. All right, so what do I do? How do I get the population in the year 2900? I could take my population in the year 2450, and I would say, okay, 450 years have passed from 2450 to 2900. 450 years have passed. How many sets of 45 years is that? 10. So for every set of 45 years, the population doubles, so I'm going to have to double 10 times. So I would multiply by 2 to the 10th here. So that 6,144 billion multiply times 2 to the 10th. Oh my goodness. Okay, so now I have 6,629,156. 6,291,456 billion, right? That's 6 million billion. I don't even know what that is, right? So, yeah. But what's the name of that place value? to the 15th. 9th is billion, 12th is trillion, so quadrillion. This is 6 quadrillion people. Or I could have started at the very beginning, at the year 2000, right? I could have started at the year 2000 and said, how many years have passed from year 0 to year 900? 900 years. How many sets of 45 are there in 900 years? 20. So I could have multiplied times 2 to the 20th, started with 6 times 2 to the 20, and you'd get the same answer. All right, so the next thing we want to figure out is the Earth's population in the year 2120. Why is this problem harder than the previous ones? Ryan, why? Because 2120 is not a multiple of 45. 120 years after the year 2000, you say, okay, how many sets of 45 years have gone by? And you go, oh, well, I figured that out by doing a division problem. Oh, 2 2/3, right? Okay. So it's going to double somewhere between 2 and 3 times, right? My population. So, so 0, 45, 90, 135, right? Those are the first few multiples of 45. 2120 is somewhere in here between 90 and 135. So my populations go 6, 12, 24, 48, right? They double every 45 years. So my population in the year 2120 should be somewhere between 24 and 48 billion. Does that seem like a logical answer? So P sub, we'll call this 120, right, for population in year 120, should be between 24 billion and 48 billion, because it's going to double somewhere between 2 and 3 times. So let's just use the same exact procedure we did before. We said, start with your 6 billion, right? And you're going to multiply by 2 some number of times, and I used an exponent to represent how many times I multiply by 2. So let's let that exponent be 2.67, right? The number of sets of 45 years that have gone by. It's not a whole number, but who cares, right? We're just following the exact same procedure we did before. It's just that that number was always a whole number before. So let's see what that comes out to. So 6 times 2 to the 2.67, and you get 38.19 billion. Okay. Is that a number that makes sense for the population in the year 2120? Yeah, why, Stephanie? Because it's between 24 and 48. Yeah, we know it should be between 24 and 48. That is somewhere between there, so that number makes sense. So this number, my exponent, this I found by taking the number of years that had passed and dividing by 45. Right? This is the number of sets of 45 years, which you get by doing a division. 120 years divided by 45 years, and that tells you the number of times you need to double. What? The 120 is from the question. Can you figure out the Earth's population in 2120? 120 is I'm using, instead of using 2000 in all of my question, I've just dropped the 2000 part to make my numbers more manageable. Okay, so before we move on to the next one, find, what was it, the Earth's population in the year 2500. Okay, so the year 2500. I've seen a couple of different approaches. Some people said, well, I know the population in 2450 because we did that earlier. Some people went all the way back to the year 2000. I knew the population was 6 billion. Either way, you'll get the same answer. So let's start in year 0, 6 billion, right? So how many years have passed from year 0, or from the year 2000 to the year 2500? 500 years. Okay, so 500 years have passed. What I need to know is how many sets of 45 have passed. So I divide by 45. Is it? It's 9.11? It's 11.11. Thought so. 11.11. All right. So if I'm starting at 6 billion, starting in the year 2000, 11.11 sets of 45 years have gone by. So that's how many times I'm going to double my population size. So that means I have my 6 billion. I'm going to double it, so that's times 2, right? Doubling it. And I'm going to multiply by 2 over and over and over again. In fact, I'm going to multiply by 2 11.11 times. So that's what the exponent does. It tells you how many times you're multiplying by 2. And that comes out to 6 times 2 to the 1.11, 12 point, oops, that's supposed to be 11.11, 6 times 2 to the 11.11, and I get 13,261 billion, right? So 13,261. I'm going to include the 0.6 because 500 million is quite a lot of people, right? So rounding to a whole number doesn't make as much sense when you're dealing with billions as regular whole numbers. So I'll put 0.6 because that's another 500 million people, 600 million people. So that's billions. All right, so another thing I saw people do is start at P sub 450, because we knew that one. 450, what was that population again? 61446, yeah. That can't be right. 61.446. Okay. Double check it. Oh, billion. 6.144 billion. That is not a 6, it's a billion. Okay. So we knew this, we knew the population here from in year 450. So I say, okay, I'm going to start with, that decimal goes there. Okay, so I'm going to start with my 6.144. Is that right? No, that can't be. It is 61, isn't it? Oh, 6,144. Okay. Woo! Place value is tough. 6,144 billion. 6,144 billion. Okay. And then I'm going to double it some number of times, right? To get from 450 to 500 years, that's 50 years. How many sets of 45 is that? 1.11. It's one and a little bit, right? 45, there's one set of 45 and a little bit more, 1.11. And that should also equal, put in your calculator, 13,261.6 billion. That's $13 trillion. I mean, people. When we start talking about numbers this big, I always think about dollars because it's almost the only thing that we think of that's that big, like the deficit, you know, in trillions. So I always start thinking dollars, but but in this case, it's people. All right, so I want to know, what is the yearly growth factor, right? So I know that every 45 years that passes, I double, so we call that the growth factor times 2. My growth factor is 2. But I only can multiply by 2 every 45 years. What should I multiply if I just want to see the increase for 1 year? Oh, you're very close. Don't switch to days. We're doing everything in years. Nope, don't switch to weeks. Keeping it all in years. 1. Yeah. So what I did before is I would say, you know, whatever I had, p sub n minus 1. I would say p sub n is p sub n minus 1 times, and if 45 years had passed, I would write times 2, right? If 90 years had passed, I would write times 2 squared. If 120 years had passed, I would write times 2 to the 2.67, right? But if 1 year has passed, I'm going to multiply by 2 to the 1 over 45, right? I want to know how many sets of 45 there are in 1, right? So 2 to the 1 over 45, this is p sub n minus 1 times 2 raised to the 1 over 45, 1.0155. So that's what you multiply by each year to increase the population from 1 year to the next, 1.0155. If I were to multiply by 1.0155 45 times, what would I get? Let's see. Let's just, if I multiply by this by itself 45 times, that's the same thing as raising it to the 45th. You get 2. Can you tell me why? Yep. So to increase my population size over 1 year, I multiply by 1.0155. If I do that 45 times, I should get times 2, because that's what you multiply by over a span of 45 years. Get the 2. All right, so multiplying by 1.0155, this is my growth factor. We call this a growth factor. But in real life, we don't often talk about growth factors. We talk about percent increase. Okay. So what does that growth factor represent in terms of a percent growth? So the 1 to the left of the decimal point, that means 100%, right? Keep 100% of the population you used to have. And the 0.0155 represents a percent growth. What percent growth is it? 1.55%. Yeah. So 1.0155 corresponds to a 1.55% growth. So it doesn't seem like that big to have the population grow by 1.5% every year. It doesn't seem like that big a deal, but we saw that over a relatively short amount of time, 400, 500 years, which is, beyond all of our lifetimes, but in the length of time the universe has existed, it's not very long, the population gets big really fast. So does this make sense where this 1.55% comes from? So you subtract the 1 because that's just the 100% that we keep. And 0.0155 to change that to is a decimal. To change it to a percent, just move the decimal point 2 to the right and multiply by 100. All right, so a bank account can be thought of as a population of money. And I want you to work in your groups, debate, discuss, which would you rather? $1 million that I just hand to you right now, or a promise that I will give you 1 penny today. I'm going to put it in a bank account for you in your name. I'm going to put in 1 penny. And every day, that bank account will double in value for 30 days. Discuss. Okay, so which would you rather? The $1 million or the penny? A penny, yeah. So if I start with 1 penny and I double 30 times, right, once a day for 30 days, then I'm multiplying by 2 30 times, or 2 to the 30th. I'll change it after. So when I multiply 1 times 2 to the 30th, yeah, so I have 1 times 2 to the 30th. Oops, that's not on. 1 times 2 to the 30th. And I get 1073 741824, comma. So that's hundreds, thousands, millions, 1,073,741,824 what's? Pennies, right? Cents. Because I started with 1 penny, double it 30 times, so this is how many pennies I have. How do you figure out how many dollars that is? Divide by 100, because there are 100 pennies for every dollar. So divide by 100, which is just moving the decimal 2 to the left. So I'm going to have 1,073,741,824 dollars. Okay, so I end up with $10,737,418.24. So this is a much better deal than the $1 million. It's 10 times as much money. So exponential growth can be referred to sometimes as compound interest. So when you earn interest on your interest, like in a bank account, we call that compound interest. And there's a famous quote that's often attributed to Albert Einstein, though I don't think that we know for sure he said it, but he said that compound interest is the most powerful force in the universe, right? That growing by a percentage or exponential growth can get big so fast that it's like a really powerful force. All right, but exponential growth is generally not sustainable with populations of living things, right? Because resources like food and water and space are always finite. So you can't just keep growing and growing and growing a population. So a more realistic population growth model is called the Logistic Curve, which levels off at a carrying capacity of the environment. So it grows really fast at first, and then it slows down as it reaches this carrying capacity, the maximum number that can live in the space that exists. So we're not going to talk about a formula for this kind of growth. Just be aware that aside from linear and exponential, this is sort of a more realistic one, but we're not going to talk about its formula. All right, so I want to spend the last 15, 20 minutes having you guys work on the activity Bacteria Are Scary. I'll come around and help as you get stuck.